Today, we're going to talk about the integral test and P-series test. And these are just more tests to determine whether or not our infinite series are going to converge or diverge. So our integral test, and there is something that is key here in our integral test. F is positive, continuous, and decreasing for all x greater than 1, and a sub n equals some function f sub n, then the series and their improper integral either both converge or diverge. Now, first thing that I want you to note is you have to prove that f is positive, continuous, and decreasing, okay? For all x greater than 1. Now, if this was something like 2, it would be for x greater than 2, okay? Now, I want you to also note that our sum, so this sum does not equal what the integral equals. It's just a test that we can use. Okay? Okay, so the integral test is use the integral test to determine convergence or divergence. So again, we need to prove that this function is positive, continuous, and decreasing. So we need to state these three conditions before we want to use the integral test. And that's really, really important. So first you have to realize that n squared plus 1 is greater than 0 for all n. So 1 over n squared plus 1 is greater than 0 for all n. Okay. 1 over, I'm going to change it to x squared plus 1 because you're actually talking about the function f of x, is continuous. Because x squared plus 1 never equals 0. Okay. And then the last thing is you need to prove that we are decreasing. Remember how we prove something's decreasing? Is we look at the derivative. So my derivative of this function is negative 1 times the quantity x squared plus 1 to the negative 2 times by the derivative of the inside. That simplifies to negative 2x over x squared plus 1, which is less than 0 for all x. So again, you have to state positive, continuous, and you have to prove that it's decreasing in order to use our integral test. So now I can use the integral test. Now I can say, not that these are equal, but I can use and remember, when we're doing improper integrals, we do that. We have to write out the limit, and then we take the antiderivative. I just did all of my antiderivative videos for my AB class. It's winter break 2020, and so I'm spending a lot of time here in my shelter in place working on videos. So as I go through all this math, so as b goes to infinity, inverse tangent goes to pi over 2, and as inverse tangent of 1 is pi over 4, so this equals pi over 4. I got a value, so I know that this converges. Okay, example number 2, that this is for n greater than 2, or n equals 2. It starts at 2 because ln of 1 would be 0. So what we want to make sure we do is we state our conditions. So we state that the function that we have. And let's try and use x's for this. ln of x is greater than 0 for all x. ln of x is continuous. If you want to write those in one statement, you can. I just realized that as I was writing it. So we're continuous. Now the derivative, I'm not going to go through all the steps of the derivative. I'm just going to look at what my final derivative was once I got it. I have all that in parentheses. Okay, since I have that, the squared is always positive. Okay, this is always less than 0 for all x greater than or equal to 2. So then I can say that I can set up my limit as b goes to infinity of my integral from 2 to b of 1 over n ln n. Realize that that is a u substitution. U equals ln n, and then you have your work. I'm not going to go through that. You guys should be able to do that. If you need to show your u substitution over on the other side, I am not going to make fun of you. I would have. I probably would have had to do that, and I think I did it over in my notes. I think wherever I stole this from, I didn't show it over in my notes. Okay, so if you notice, as b goes to infinity, the ln of b is going to be infinity. The ln of infinity, this is going to be infinity. So this diverges. So therefore, this diverges. Okay, next example. Determine whether this series converges or diverges. So I'm going to try this integral test because that's the one we're talking about here. So this function turns into this, which simplifies to that. This is definitely not increasing. It's continuous, it's greater than 0, but if I were to take the derivative of that, this is greater than, this is not decreasing. So therefore, our test, we can't use the integral test. So we have to use a different test. The only other test that we have is that nth term test for divergence. Remember, I always struggle with that one, so I will be often rewriting it. So remember that said that if the limit as n goes to infinity of this function doesn't equal 0 or does not exist, then this diverges. So let's look at this limit. So the limit as n goes to infinity of this function, which is really e to the x squared, well, as n goes to infinity, that's going to get big, that's going to get infinitely big. So it's infinity, this does not exist. So we can conclude that this diverges by the nth term test. And it's a good habit, and I was poor at it in this video. Make sure you write out the test where it diverges by or converges by? Okay. P-series and harmonic series. So this is very similar to that p-test that we had when we were doing improper integrals, and that's why I preface it in that video or in that lesson. So you have a positive constant, remember that is called a p-series. You have a p-series test. If p is greater than 1, then our series converges. If it's between 0 and 1, then that series diverges. And remember that you have a harmonic series, or a special type of p-series. It's called a harmonic series when p is equal to 1, and that is going to diverge. Diverge. Okay, so our harmonic series diverges, and you can say this series is harmonic, therefore it diverges. Okay, this example. So I have 3 over n to the first times by n to the 1/2. I'm going to rewrite, I'm going to make sure I'm a good student, and I do that. So I add my exponents when I'm multiplying. So then we can say that, and I should maybe, in my notes, I have this 3 pulled out in front. I don't think it really matters, but 3/2, p equals 3/2, which is greater than 1. So by the p-series test, converges. Now this one, I like this one. I was going to not give you guys this example, but I like this one because it's some crazy exponents happening in there. I have n to the third times by n to the negative 11/3. So that's going to simplify to, I add my exponents, and I get 1 over n to the 2/3. Okay, and so now we have 2/3, which is what p equals, which is less than 1. So by the p series, I can't write. Let's just rewrite this. By the p series test, our series diverges. Okay, last question, and this is often a fun question for a multiple choice. They'd give you a bunch of options. For what values of p will this converge? So remember that your exponent has to be greater than 1, has to be greater than 0, so p has to be greater than 0. So that is our integral and our p-series test. I hope you enjoyed that, and thanks for watching.